Welcome to the Futureering podcast. My name is Philip Sarek. The aim with this podcast is to highlight some of the incredible science, technology, and innovation happening in Australia, and some of the key individuals who are helping to build the future. This podcast is sponsored by Neurotech. Neurotech have created Enhance, Australia's most advanced and comprehensive nootropic formula. Enhance is a nootropic, or brain supplement, that combines 10 natural ingredients, including B vitamins, plant extracts, and amino acids to help support your mind each day. In particular, Enhance can help support and enhance your mental alertness, your focus and clarity, help maintain your nervous system health, and support your energy production. Enhance is also a listed medicine on the Australian Register of Therapeutic Goods. This means that it has been formulated, manufactured, and lab tested to some of the most stringent standards in the world. Neurotech also offers a 100-day, 100% money-back guarantee. So if Enhance doesn't work for you or you don't love it, you will get your money back. Listeners of this podcast can get 15% off today for Enhanced Nootropic by simply using the code FUTUREERING. Just visit www.neurotech.com.au and use the code FUTUREERING to get 15% off Enhanced Nootropic. In today's episode of the Futureering podcast, I'm speaking with Professor Allan Paull. Now, Allan Paull is the DSTG Chair of Future Hypersonic Technologies at the University of Queensland. Allan first completed his Bachelor of Science in Applied Physics and a PhD in Applied Mathematics at the University of Queensland in 1987. He is now a world-leading expert in hypersonics and scramjet technology, which has applications for access to space, defense, and potentially international travel in the future. He was the international program leader for the HYSHOT Scramjet Test Program at UQ and was the first person in the world to achieve the first successful test flight of a scramjet engine, reaching speeds of up to 2.3 kilometers per second, or Mach 7.6. I've known Allan from my time studying at the University of Queensland when I was initially exposed to hypersonics and scramjet technology. And I'm excited to have Allan join me on today's podcast. Could you just give our audience, for those who don't know much about you or your work or your research, could you give us a bit of an introduction as to your journey so far from sort of studying at university to where you are now working in aerospace and hypersonics, and just give a bit of background there?
Okay, that's a bit of a long journey, but anyway, I studied applied maths at the University of Queensland and completed an applied maths degree after 4 years, and then went on to do a PhD in applied maths. And after that, I got a job in the mechanical engineering department testing scramjets in the shock tunnel there under Ray Stalker, well-known Australian, that started Hypersonics. And that went on for quite a number of years, and we were developing engines that were started to produce more thrust than drag, so they're actually operational. And then we ran into a lot of problem that people didn't believe our test time or our data, because they were very short test times that we had, which was down in the milliseconds. And we had to do a flight test essentially to demonstrate whether our data was correct or not. So a lot of things went under through, and we eventually managed to secure a couple of rockets from the US. It was coincidence that it occurred through a group called Astrotech in those days in the US. We ended up doing some flight tests out of Woomera to demonstrate whether our combustion tests were valid in the tunnel. And then people realized that the approach we had done was something which would be applicable to more detailed testing in flight. And then it opened up a very cost-effective way of doing it. So that went on, and I ended up doing a whole bunch of flight tests for the university, and then transitioned to defence and did quite a number of flight tests under the HYFire program with them. And now I'm back at the University of Queensland looking for new types of propulsion systems. So it's a long and twisted path. Nothing planned, I might add either.
Yeah, that's a crazy journey. I'm very much interested in sort of your work with the HYSHOT program. So am I correct in saying you're one of the first people involved with proving sort of the operation of a scramjet engine during HYSHOT?
Well, HYSHOT was the first flight program where we were attempting to demonstrate the the combustion data that we were seeing in the tunnels, or find the correlation between the combustion data we're seeing in the tunnels and flight. And it turns out it was 1-to-1. What we did do is in the tunnels, we demonstrated propulsion. We were the first to demonstrate a scramjet that was actually producing more thrust than drag. But the HYSHOT program was much more scientific in the sense that it was only to demonstrate that correlation between flight and the tunnels. The engines we were flying wouldn't produce thrust. They were never designed to. And in fact, the reality is in flight, I've never actually flown an engine. It's always been some sort of experimental concept which demonstrates a certain principle.
Yeah, okay. So what was that sort of jump when you went from studying applied mathematics to getting deep into aerospace and hypersonics? What first drew you into following that path of going into aerospace?
The truth of the matter was I didn't have a job. And so it was, I was hungry, so I needed the job. And, that was one of the driving factors. But the other thing was I was more practical rather than theoretical. And although I had a strong background in the theory, I really was urging to do something more practical with that theory. And so the move to a more experimental type environment, which was offered to me, was a fairly easy thing to make. So, and that turned out to be in the aerospace. To be honest with you, I was all, as a kid, I was always making planes and all that sort of stuff. So it wasn't too far-fetched, but, could have been anything else too, I was also designing cars and a thing like that. And I was interested in electric vehicles way back then. So there were, it was really just things just fitted nicely. And, I was happy with what I was doing. It was exciting. And why not? Then you get wrapped up and caught in it. And then 40 years later, you're still doing it, right?
Yeah, absolutely. So we're throwing around a few different terms here that a lot of people that aren't sort of in this field might not quite understand completely, such as hypersonics and scramjets. So let's break those down a bit for people if we can. And I want to hear from you, like what is hypersonics exactly, and how does it differ from other flight regimes such as subsonic and supersonic that people are probably more familiar with?
All right, well, let's start at the bottom. Subsonic, I think everyone's familiar with that. It's flying at speeds up to Mach 1, where Mach 1 is the speed of sound, right? And that's around about 1,000 kilometers per hour. It depends where you are in the atmosphere, but 1,000 kilometers is good enough. Then when you transition above to high speeds above Mach 1, so in other words, you're going more than the speed of sound, the equations change, the equations and the physics, which, are reflected in the equations, change enormously. And that's called supersonic flight. And supersonic flight, by definition, is everything above Mach 1. But what happens when you get up to about Mach 5 is a lot of the equations collapse and the phenomena you see start looking the same. Right? Not everything, but a lot of things do. So above Mach 5, if you were looking to see where, say, a shock wave, which is you hear about the sonic booms and things like that with supersonic aircraft. Well, that's just a shock wave. Yeah. Where they would lie on an aircraft doesn't vary that much between above Mach 5. So as a result, there's a simplification actually, and that's called the hypersonic regime above Mach 5. But then there's a lot of theory that sits above that where the air starts to break down with the temperatures involved as you fly through it. The temperatures that end up on the surface of the vehicle get hotter and hotter. The air breaks down, and eventually, there's a whole bunch of regimes above that, and you end up in actually the final regime, which is called the hypervelocity regime, where you're at speeds of greater than 5 kilometers per second, which is Mach 5's around considerably less. Let me put it that way. So it's at Mach 5 rather than 5 kilometers per second. So you can see that there's all these different regimes, but it's basically the different physics is driving it. And And from the terms of hypersonics, which is well splashed around right now, it's really above Mach 5 and probably realistically below Mach about Mach 10, where basic things sort of stay the same.
Yeah. Awesome. That was a good breakdown. And what about a scramjet? So a lot of people know of more traditional propulsion forms such as, a jet turbine or a rocket, but scramjets are sort of popping in. People are hearing about it on the news.
Yeah, okay then.
It's becoming more popular and it's starting to be a bit more commercialized. We're getting to that stage. Can you break down what exactly scramjet is?
Yeah, okay. So we all know a jet turbine. We've been on a plane, look out the wing, there's one hanging underneath it. And these are air-breathing engines. Now let's dissociate ourselves with rockets, which are not air-breathing. The rockets carry their oxygen with them and in some form or other, and they can operate outside the atmosphere. Turbines obviously cannot. They're just like a car engine. They suck the oxygen in and combine it with the fuel, and that in this case is probably some form of kerosene. And the release of energy is then basically changed into pushing the vehicle along. So the next stage up though is what they call a ramjet. Now a turbine uses that big turbine blade at the front to compress the air. Because in a car engine you need to compress the air, and that's what the pistons do. They compress the air, and a diesel is an example. It compresses it and heats it, and so at a high pressure, high temperature, it burns. Well, the turbine's doing the same thing in a turbine engine. But if you go fast enough, when you have an inlet and you compress the air in the inlet, then the temperature also rises. And you can think of the inlet surfaces sort of like the piston in your car. But what happens then is you get air flowing through the engine, and this is called a ramjet. And you're basically ramming the air in, and it's getting hot. And then you throw the fuel in, and it burns, right? But if you're going sort of to about Mach 5, and the flow through the engine is always subsonic. So when you compress the air, you compress it in a way, even though you're flying supersonic, it just forms what they call a bow shock around the front of it, and that compresses the air, but it's always subsonic. Now you can keep doing that if you go fast enough, above Mach 5, but the trouble is the air gets too hot, and if the air gets too hot, you actually cannot burn what you think of traditionally burn. It won't release its energy. It's just too hot. So what you've got to do is not have a big bow shock around the front of it. You've got to let the air flow through it in supersonically all the way, and that allows you to burn at a lower temperature. And those things are called scramjets. And it's actually supersonic combustion ramjet is what it's short for. So it's just the way you have to burn this fuel when you go faster and faster. And it kicks in around about Mach 5. However, even there's a transition. And there's pure scramjets, which exist above about Mach 7. And there's things called dual mode scramjets, which exist around the Mach 5 to 7 region. So there's a finer thing in there as well. So anyway, but yeah, they're basically just different air-breathing engines. And as I said, a rocket is a completely different story again, and it's only really it's a different physics totally, and we shouldn't confuse the two.
Yeah, absolutely. That's awesome. So what are some of the applications of scramjet technology and propulsion? Where can we actually find a good use for that?
Well, there's two. There's a group in Brisbane called Hypersonics, or Hypersonic, and they're trying to develop a hydrogen fueled scramjet for access to space. Now, the original approach to develop scramjets was from the original recent one was from the NASA program in the 1990s, where the Americans, or under NASA, they were trying to develop a single stage to orbit vehicle, and the scramjet was touted as being that engine. That didn't go so well. When you look at the physics, it's probably pretty obvious why it didn't go so well, the physics we know now. But Hypersonics is persisting not with that approach, but with an approach where the scramjet's the second stage. And there's sufficient gains in this so as to make it reusable, and therefore it's cheaper, and also the turnaround time's a lot quicker. So it's a different approach which has got a lot of merit. The other approach, of course, is we all hear about it. Defence departments worldwide are looking at the technology so as to develop long-range, high-speed weapons. And so you don't deny that that's also a part of what a scramjet can be used for.
Yeah, absolutely. Yeah, there is a few very interesting applications for it, and as I said, it's starting to become more popularized, I guess, and people are starting to learn more about it, which is exciting. Something we've spoken about before, and something I'm quite interested in, and I want you to go a bit deeper into that on this podcast if we can. But there's a lot of obviously interesting research and innovation being done at universities and within academia. How do you think we can best get that research out of academia and into tangible products that can benefit humanity? Because there seems to be a bit of a gap there between all this great stuff that Australia is doing in terms of research and actually commercializing into products that can be used.
Well, actually that's a very good question, and I've pondered this as well. And there's a thing called technical readiness levels. And just to give you, it's a scale, right, on how ready you are. Technical TRL1, which is technical readiness level 1, is basically I've got a good idea, right? I was in the shower and I had a good idea. And you do a bit of basic stuff. Now, TRL9 is it's a fully operational system and you're basically servicing it, right? So that's going from the beginning to the end. Typically, universities work up to technical TRLs 3 and 4, where they've demonstrated stuff in the lab, right? And then typically industry takes over at technical level 6 and 7, where 6 is where you've demonstrated it in real life, and 7 is when you start going towards production, developing techniques to produce it. And the valley of death is what people talk about, which is what you can't get through. This is TRL 3 to 4 to TRL 6 to 7. So if you really, and this is where you're transitioning from in the lab to a demonstration, in the real world. And in my case, it's saying, basically doing theoretical studies and doing wind tunnel tests, and then taking that to a flight test. That's an example. So you're asking the question, how do you get over the valley of death? Well, what you need is two things, actually. Yep. You need a workforce to help you, right? And generally speaking, they're younger people. And you need a mechanism which allows an academic, or let's say it's an academic for argument's sake, it doesn't have to be, but allows them to collaborate with industry and industry to collaborate with them in a manner which is industry, doesn't have to pay a bucket load of money, because otherwise it's got to recuperate and there's a barrier to it. But at the same time, the academic, it can't be living on the street either. So there needs to be a well-tuned mechanism for taking that theory and putting it in flight or in a practice. Now, so what I did, what I saw as an example of how to do that was there's a lot of work around at the universities, all the universities, which is really extremely good, but it doesn't get that chance to go to my case, the flight test. So I said if we could get a bunch of small rocket motors and get the kids that are, coming out of the universities and train them up with the rocket motors, train them up to design flight vehicles, which incorporated the scientific requirements of this new gadget or whatever, and then fly that at a suitable place, then that would, and have that mechanism well sorted. So in other words, you've got launch ranges sorted out, you've got the administrative requirements sorted out, the safety sorted out, in some cases the security sorted out, if you've got all that mechanism in place, there is a way to transition this and to demonstrate that capability, good or bad, and do it in front of the customer as well as the prime or whoever that's going to actually take this further if they can. So put that whole thing in place. It's not trivial, but if you think about it and you've done it already, then it is a fairly easy thing to set up with really quite a small amount of money. And you've got to set up the SMEs to support you as well. In my case, I needed the SMEs in Australia to build rocket motors because no point importing them. And I needed launch ranges and I need launches, and we're not all there yet, but we are getting that way. And I need enthusiasm from the powers to be to actually want to do it. Right? The powers to be, our governments of the day, say they want to do it, but you've got to put your money where your mouth is too. If someone's offering you to do it, then you can't turn around and say, "I'll wait," because those people, people like myself would get very disillusioned. So, if you are offered solution, the government has to come up with the money because it's just part of the education system and being extended into industry. It's bridging a gap, and it's small money. It is small money. You're not talking hundreds of millions of dollars. You're probably talking, in the orders of $10 million over quite a, say 2 to 3 years. So these kids that come out of university, you can't say you're going to work for nothing because they're not responsible to you. You've got to actually pay them money, pay them a basic or a wage that they get in industry. A fair wage. Because otherwise, you've got no ability to actually control them. Students are not controllable people, I'm afraid, right? They do it on their own time. They do what they want to do. But if you're actually paying them, and although they'll be enthusiastic, you do have some sort of levers there. And so you've got to pay those people, and that's your biggest bill. And then you've got to have the SMEs to support you. And this is not only rocket motors, but, in my case, it's, high-tech materials, suppliers that supply electronics, all this sort of stuff. It just goes on and on. I think we've got 100 suppliers lined up. There's supply chains and all that sort of stuff. So it's the whole kit and caboodle, and you need to set all that up. But if you know what you're doing, it's not that hard.
Yeah. I like how you said sort of we need a good mechanism, I guess, to facilitate like a streamlined collaboration between the research and government and industry, as well as the funding, and find a way to put it all together in a way that makes sense to really, I guess, accelerate commercialization and, create these tangible outcomes. I think that's super important and something we need to focus on as a nation for sure.
Well, I think it.
So I would love to ask you, so what?
I think it's everything that every Western nation actually is striving to do.
Yeah, absolutely. So what do you see as sort of the future of propulsion technologies or scramjet technologies? Is there anything new on the horizon, or is sort of scramjet sort of the pinnacle of what we're doing right now?
Well, I think scramjets have, they're still, I wouldn't say experimental. They have advanced up the TRL ladder, and they're approaching, or we've demonstrated. I demonstrated with the Hi-Fi group and HYSHOT group and HyCores group that we demonstrated certain aspects of the engines. Are they the pinnacle? I think that you're asking the question, what's next? And we all know that electric propulsion, and all you got to do is look at the automotive industry and you know what's coming. Electric propulsion, we're moving towards that.
Yeah.
Not only because it's we need it for our greenhouse gases, but the reality is it's also a better way. It gives you more performance, and it's simpler, and ultimately it'll be cheaper. So that's also I think where propulsion's heading. We see it with aircraft now. The subsonic ones, we see small aircraft that have been fielded right now, which are electric propelled. And there is no scientific reason that you couldn't go up to the higher speed with it. Eventually, you'll run into materials issues. You just don't have the materials, because what happens as you go faster is there's a lot more stress on the materials, and eventually you run into that problem, no matter which technology. So, but the point is, you can go towards electric propulsion, and there's different experimental systems being investigated to, work at the supersonic regime up to about Mach 5, maybe 6. But there's also work that's being done at the much higher Mach numbers, Mach 10, even up to Mach 14, which is electric. And when you combine this with some advanced technologies like superconductors, and some of the really high-tech materials that we have, not like we don't have it, we do have it. You start saying, oh, hang on, there's quite a number of different solutions up here, and that we haven't explored. So I think the bottom line is propulsion systems will go electric. I think the energy sources is always going to be problematic. Initially, if we follow a chemical type approach. If you follow a nuclear type approach, that may, in the future, become safe enough to do. That's a bit fair way off, I think. But there is also something in between the two called leptonic fuel supplies, where you're talking about natural decay of certain elements, and that also produces sufficient power used in certain ways. And it's quite an interesting thing. So the energy sources are starting to come forward. The electric propulsion systems are starting to be developed. They're at pretty low TRLs, but they're getting there. And so I think your answer to your question is, in the future, we will see electric propulsion of some form or other. And the scramjets aren't at the pinnacle. They are a stepping stone to the high-speed flight.
Yeah.
But I think, in the future, there's going to be something different again.
Yeah, that all sounds super exciting, and a lot of people are getting interested in, I think, sort of aerospace and space and propulsion. So do you have any advice for anyone wanting to get into aerospace, whether they're, a high school student or someone at university? What advice would you give in terms of what should they be studying at university? Do you think they should go into research like you did and get a PhD, or maybe go straight into industry? Do you have any advice there for anyone?
Well, yeah, I suppose the answer to that is you must follow what you like, right? Not what your parents like, not what you think is a good idea, but actually what you like. Now, in the space industry, per se, there is a career in just about anything you want to study. Sure, if you study the sciences and the engineering, you're going to be in a good place, right? But if your passion is law, as an example, there's plenty of room for you in that space. You have, just say you were really passionate about law, but you kind of like space as well. Well, there's space law, and there's all sorts of things out there that are just growing. So my advice to someone at high school is just follow. If you like doing something, and therefore you're generally good at it, just follow that, right?
Yep.
Go to a good university. That's kind of important. Money is probably very wisely spent if you go to a good university, and most of Australia's got, pretty good universities. So from that perspective, it's not a big deal. The thing is then, if you're good enough, when you finish 3 or 4 years at the university, or 5, then I would say that it's a good idea to go to a higher degree, like a master's. So I'd go straight to a PhD if you're good enough. However, that's not necessary, and the backbone of the workforce that's actually driving all the technology now, they although the PhDs are some of the powerhouses, there's a lot of people, the majority of people don't have PhDs. They might have masters, but they're really just driven people that are damn good at what they do. And, I've got some very, very good engineers that have worked for me. They're capable of doing a PhD, but they've chosen at this stage not to. And, but, their talents are well appreciated, and you can get the job done. And everybody's got their place to play, part to play in all this work. So follow your passion. How high you go is up to you. The only other thing I'd say is don't look for the adverts. Go and put your foot in the door of an area you like. I don't want to get 1,000 emails, but you look for the people that you feel that are in the area of interest to you, and go and knock on their door. And even if you're in undergrad or even at high school, we still reach out right down to high school. Is there something I can do? Go up to them. Is there something I can do to be involved? And there generally is something. And usually you'll get paid to some level. So, it's like a part-time job. So I'd look at that. You just got to be involved and be seen to be involved and be seen to be enthusiastic. And, by doing it, you might get, God, I don't want to do that. That's awfully boring. And that might change your mind. Or you might just get so enthusiastic about it. And, as someone that employs people, do I look at the resumes? Well, kind of, but what I look for is enthusiasm. So, we can always work with enthusiasm.
Yeah, absolutely. That's some great advice. It is sort of finding that intersection of, what you're super passionate about and what you love, and then also your strengths as well. And also just not being afraid to, as you said, knock on the doors of the people, the experts, and reaching out, asking the questions. And even getting stuck into a certain field and seeing if you actually like it, and then, iterating or changing from there, because you don't really know unless you're in it and you give it a shot.
That's right.
I want to also ask, do you have any key lessons that you would tell your younger self? Obviously, you have a lot of experience and wisdom now, having spent a lot of your life doing this work. Is there anything you would go back and tell yourself?
Yeah, people ask you that question, and I struggle with that. It's either too much or, I suppose really, I've had a pretty good career, and what, I suppose the things that I worried about was self-doubt. Was I good enough? Right? And if you look at that, that's just a stupid thing to say, right? You're as good as you are, and you're going to get to where you're going to get to, right? So the answer is that's what I would say to myself. Don't worry about it. She'll be right. You'll get there. And you'll, the important thing is to get there and to enjoy getting there. And, like what you're doing. So what I tell my younger self is she'll be right. Let nature take its course and you'll get there.
I love that. I think as someone who stresses a lot about the future, and I think a lot of people do, that resonates a lot with me. Just, you'll be right. Just enjoy the journey and follow a path, and you'll be okay in the end.
Yeah.
This is another one of my favorite questions to ask. I don't know if you're big into reading or reading any books. I'd love to know if you are, what are your top 3 favorite books?
Well, I'm not, I'll be honest with you. I enjoy reading books, but I'm not an avid reader of books per se. I tend to read a lot of stuff that is related to the work, right? But if you ask me what books I've really enjoyed, I must admit I enjoyed reading, even Harry Potter to the kids. Like that was pretty good, right? It's just this crazy world, right? But sometimes you can dream about that. I enjoyed, there's various books about the Apollo 13 mission. I've enjoyed that, and I also enjoyed, funny enough, it just escaped my mind, but the young Australian girl that sailed around the world, Jessica Watson. I read her book, and
Yes.
well, I do a lot of sailing as well, and I've sailed up. I actually read her book while I was sailing up the Queensland coast, and thinking how bad, how rough, well, not even how rough, but it's pretty taxing at times. But it was nothing compared to what she was up against, and I quite enjoyed that the book and how it basically she just kept going, and eventually got there. Right, that was what it was all about. So yeah, I enjoyed that book quite a lot.
Mm-hmm.
But generally speaking, I can read whatever I like, and then if I get bored with it, I shut it and leave it. That's not an avid reader, but
yeah, it's the best way to do it. Okay, so to just close off, I want to ask, is there anywhere our listeners could go to find out more about you or your work or your research? If they want to learn more about sort of what you've been involved in, or if they're maybe interested in
pretty well
going down the aerospace path or the research path?
There's been if you Google my name, I think you'll probably find a fair bit. There is another Allan Paull floating around.
Yeah.
It's down in Melbourne, but yeah, I think you can do that. If you're interested in the scientific papers, well, again, you can go through a literature search there, and there's probably plenty there. But as for a book or something like that, no, I don't have a book or anything like that. We had various cracks at people talking to me about that, but no, there's nothing like that. There are a couple of actually, there's a TEDx talk. You can Google that. That's a talk of a different approach to things, but it's on the same sort of subject. So yeah, you could TEDx talk, I suppose. Just Google that, you'll find something. And but yeah, just look around different articles. They'll see what I've done and all that sort of stuff. And then of course there's LinkedIn and all that sort of stuff. It's got some basic things, and you'll also see there's a couple of websites based on building a boat, building a sailing boat, and then sailing a sailing boat. So Bush Spirit's the name of the boat. So if you Google Bush Spirit, and you might find a few different articles rather than anything scientific. So that gives you a bit of an idea.
Yeah, fantastic. Yeah, I definitely recommend the TEDx talk. That's a great resource, I think, for people to learn a bit more about you and your work. I found it very fascinating myself personally. So I think, we'll wrap it up there. That was a good little podcast. Hopefully help some people learn more about aerospace, scramjets, hypersonics, and that whole interesting field that's really on the rise right now. So I just want to say thank you, Allan, for taking the time out of your day to come chat with me. And had a great time.
All right, no problems. Hope it helps. See you later.